Hi everyone, in this video we're going to finish up section 3.5, which was about the hypergeometric and negative binomial distribution. So we've had some practice now with the hypergeometric distribution, and we're going to move on to the negative binomial. But before that, I forgot to include this in the last video, and so I'm going to do that now. The mean and variance of a hypergeometric distribution. Okay, and so like the binomial that we found before, they have nice formulas, although maybe not necessarily as nice as the binomial. But the expected value is n times capital M over capital N, and then the variance has quite a long formula, okay, but it is that. And so these are important to know, or maybe have written down on a card, so that if I ask you, you can just sort of plug and chug for the mean and the variance. All right, so now last distribution in section 3.5 is called the negative binomial distribution. It's been a while since we've talked about the negative binomial. So here are the assumptions of the experiment. Again, what I said before about the negative binomial was that instead of counting the number of successes in n trials like the binomial distribution, the negative binomial is counting the number of failures until I get to a certain number of successes. Okay, so maybe like how long is it going to take me, how many trials is it going to take me, or how many failures, until I get to the fifth success. This is important in a number of different fields, maybe like in trying to recruit people to be in clinical trials for any number of diseases. They're going to bring people in, and these people could either say yes or no, whether they want to be in the clinical trial. But in order to get a specified level of significance in the statistical sense that we'll learn about later on in this course, you need a certain sample size. You need a certain number of people to get into this trial. And so it's important, the negative binomial distribution can give you an idea of how long that's going to take. So the first assumption in a negative binomial experiment is that it consists of a sequence of independent trials. These assumptions are going to look very similar to the ones for the binomial distribution. So we've got independent trials, meaning one does not affect the other. There are only two possible outcomes, success and failure. Great. The probability of success remains constant, which is what we're used to. And then the fourth one that's different from the binomial distribution assumption is that the experiment continues until a total of R successes have been observed. Okay, so we need to know how many successes that we need in order to calculate our probabilities that we want. So here's where I'm going to list out the actual distribution, so on and so forth. The random variable for a negative binomial situation is going to be counting the number of failures until the rth success. Number of failures until the rth success. Now, it's important to keep in mind, if you look this distribution up online, there are actually a couple of ways that people use this negative binomial distribution, or rather they set it up differently. So instead of counting the number of failures until the rth success, they may be counting something different, and that's going to lead to a different distribution, and it's going to lead to a whole bunch of different things. So pay attention if you do look stuff up on outside sources, that you are looking at the same negative binomial distribution that I'm talking about here. So two parameters for the negative binomial distribution. This says hypergeometric, but it should say negative binomial. The first one is R, and that's the number of successes that we want to reach. And then the second one, just like the binomial, is the probability of success. So instead of N and P, we now have R and P. We denote a random variable that has a negative binomial distribution, like this, with the tilde, okay, where you put the parameters inside the parentheses next to whatever you want to call that distribution. Okay, and the PMF looks like this. Similar to the binomial, but the numbers, of course, are different. Right? So you have x plus r minus 1 choose r minus 1 times p to the r, 1 minus p to the x. I won't go through and actually talk about each of those parts because they mimic very similarly the binomial one. But of course, they're different. So I know I'm going to have r successes, and then I have however many failures it takes to get to the rth success. So p to the r, success, 1 minus p to the x, failures, the choose, how many ways that can happen. Here, x is an integer, and x can go on technically forever. Okay, so if I have something that's really unlikely to happen, and I'm asking how many failures it takes to get to like the 10th thing of something that doesn't happen very much, I can have a bunch of failures. So technically it can be infinite number of failures before I get to the rth success. All right, so this is the example I'm going to do. A pediatrician wants to recruit 5 couples, each of whom is expecting their first child to participate in a new natural childbirth regimen. Let the probability of success be the probability a randomly selected couple agrees to participate. Right? So if p equals 0.2, which means it's a 20% chance that they actually agree, what is the probability that 15 couples must be asked before 5 are found who participate? Okay. And so they clarify what they mean there. That is, if the success is they agree to participate, what's the probability that I have to go through 10 failures before I get my 5th success? And so what that means, or let's write down the important parts of this before we go to mini tab. We know the 3 important things here is we need to have x, we need to have r, and we need to have p. We know that the probability of success, p, is 0.2. We know we want to get to the 5th success, and we're looking specifically at getting 10 failures before the 5th success. And so we just take these 3 numbers and substitute them into Minitab. So let's go to calculate probability distributions. Again, we're just looking at a density, but we can do stuff with the cumulative probability, but probability density, a single value. We want to first choose negative binomial, which is right here. The event probability is 0.2. Number of events that we need is 5. That's R. Okay, and we want the model to be, so here's the 2 different ways that you can do it. Okay, we're putting in 10 here, and in fact, we are looking for, I think, only the number of non-events. So let's see what this gives us. Okay, so here we have p equals 0.2, r equals 5, and we want x to be 10. Great, so our probability is that there's a 3.4% chance, or 0.034, that it will take 10 failures before the 5th success. Okay, it says, note down here, x is equal to the number of non-events. I could do the same thing. I could go back here and say probability distributions, density, and instead of having the number of non-events, I could say the total number of trials and change 10 to 15 because it also gave us that. And if I click OK, x is going to change to 15. Probability is going to be the same. So it doesn't change the actual probability, but you need to remember what you're actually substituting in for x. So do you want x be the number of failures before the first success, or do you want x to be the total number of trials before you get there? For us, it's the number of failures, but if you know the total number of trials, you can put that in as well. And that actually marks the end of section 3.5. I'm not going to give you a your turn here, just because I think you've done a bunch and you've got pretty familiar with Minitab, and so I don't want to give you another one. But certainly we can go over more examples in class if you want to see how to do maybe a cumulative probability with this kind of stuff. Okay, but if not, that's all I've got for this video.